Yes, my dear friends, welcome back to our YouTube channel. This is the diagonalization of a 3 by 3 matrix. But this matrix will give the repeated eigenvalues. So, the purpose of discussing this matrix, this comes under repeated eigenvalues. So, under the repeated eigenvalues, what is the technique to get the eigenvectors? Particularly, they are pairwise orthogonal. It's very important. Pairwise orthogonal vectors under the repeated eigenvalues. As usually, the eigenvalues of A by using the characteristic equation lambda cube minus s1 lambda squared plus s2 lambda minus s3 equal to 0. S1 is the sum of the leading diagonal elements, 2 plus 2 plus 2, 6. And S2 is S through the minus through the diagonals. So it is 2 to 4, 4 minus 1 is 3. For this one, again 4 minus 1, 3. For this one, again 4 minus 1, 3. So it is 9. And S3 is the determinant of the matrix. 2 into 2 to 4 minus 1 is 3. So 6 minus plus 1 into this row and this column. So minus 2 plus 1 is right. Then plus 1 into minus of minus plus 1, 1 minus 2. So we get minus 2 minus 2. I think minus 2 plus 1. Minus 2 plus 1 is minus 1. Then this is also minus 1. So 6 minus 1 minus 1 is plus 4. So to substitute S1 equal to 6, S2 equal to 9, S3 equal to 4. I find out this is the characteristic equation. By using the long division method, if I see that it's a constant term, it's an even number. It's an even number. So let us try with the plus 2. So 2, let's go for 0. 1 plus 0, 1. 1 2s are 2, 2. Minus 6 plus 2 is minus 4. Minus 4 into 2 is minus 8. 9 minus is 1. 1 into 2. Sorry, we won't get here 0. So this is the wrong root. It's called trial and error. So this is, we get the error now. So plus 2 is not the right answer. So what about the minus 2? Let us try minus 2 because I thought it is even number. So I go for minus 2 here. 1 plus 0, 1. 1 into minus 2 is minus 2. You get minus 8. Minus of minus plus 16. 16 plus 9 is 25. 25 is minus 100. You get minus 104. Again, this is not the perfect divisor. So minus 2 is also not the right answer. So that's why this method is often called as trial and error method. So I tried plus 2 minus 2. This will not works. So what are the other factors of 4? Can we go for 4 itself? Because sometimes maybe works. 4. 1 into 4 is 4. Minus 6 plus 4 is minus 2. Minus 2 is minus, right? Minus 8. 1. 1 4 is 4. Yes, correct. So lambda 1 is 4 is the right answer. What about the reduced polynomial? Lambda squared minus 2 lambda plus 1 equal to 0. So it's nothing but lambda minus 1 into lambda minus 1 equal to 0. Yes, right? Minus minus 1 minus 2 minus a minus plus 1. So the roots are 1 comma 1. So finally, what are the eigenvalues of the given matrix? 4, lambda 2 is equal to 1 and lambda 3 is equal to 1. So among the 3, 2 are repeated. So I always consider the repeated eigenvalues of the second case. Got it? Right? Now, the corresponding eigenvectors. So, step number 2. So, before going to that, diagonalize the matrix, this one, by using an orthogonal transformation. So, once we found the eigenvalues 4, 1, 1, probably my answer is D is equal to, D is equal to 4, 0, 0, 0, 1, 0, 0, 0, 1. So this is my probable answer because once we get the eigenvalues, yeah, the leading diagonal elements are nothing but the eigenvalues of A. So for 1, 1. Now, how to get the eigenvectors? So let us subtract the lambda from the given matrix diagonally. So 2 minus lambda x1 minus x2 plus x3 minus x1 plus 2 minus lambda x2 minus x3 0. x1 minus x2 plus 2 minus lambda x3 equals 0. This is my star equation. Let us substitute lambda equal to 4 as the case number 1. By putting lambda equal to 4, 2 minus 4 is minus 2x1 minus x2 plus x3 and minus x1 plus 2 minus lambda 2 minus 4 minus 2x2 minus x3 0. So once we get these two equations are distinct, apply the cross multiplication rule starting from the middle variable minus 1 minus 2, 1 minus 1, minus 2 minus 1, minus 1 2. This will give x1 by plus 1 minus 1 minus plus 2, x2 by minus 1 minus 2, x3 by plus 4 minus 1, 3 minus 3, 3, multiply by 3 we get 1 minus 1 1. So this is the first eigenvector corresponding to lambda equal to 4. Now what about the second one? What about the second case? Case number 2. So case number 2 for lambda equal to 2. Let us see that lambda 2 is 1, lambda 3 is also 1. Please kindly see that both are equal eigenvalue, but I need the eigenvector which is pairwise orthogonal. That is very, very important. So the case number 2 for lambda equal to 1, substitute lambda equal to 1 here, we get this x1 minus x2 plus x3 equal to 0. What about here? Minus x1 plus 2x2, I think 2 minus 1, x2 minus x3 is equal to 0. Third one, x1 minus x2 plus x3 is equal to 0. Please note it down. These equations are identical. These equations are same. Isn't it? It's right? These equations are same. Let's see the first one. I think when I multiply the minus sign, we get the same. The third one is similar to the first one. So from this, I am getting the eigenvector by assuming that if I assume that x1 0, what I am getting that? Minus x2 plus x3 is equal to 0. That means that minus x2 is equal to minus x3. Otherwise x2 and x3 are same with the coefficients 1. So my x2 is 0 1 1. Usually when we substitute x2 0, we get the third eigenvector. Substitute x3 0, we get the third eigenvector. Continue like that by assuming that x1 0, x2 0, x3 0. But in this case, the very important thing is to get the diagonal matrix, the eigenvectors must be pairwise orthogonal. So let us think about it. We are not just getting the eigenvectors. Our aim is to make the diagonalization. Once we need the diagonal matrix, the eigenvectors must be pairwise orthogonal. So I am not going to substitute x2 0 or x3 0. We may get some eigenvectors, but I do not know whether they are pairwise orthogonal or not. There is no guarantee for it. So what I suggest you that once we get the x1, right? Now x2, what's the x2 now? 0 1 1. So let us choose the third eigenvector. Let us choose the third eigenvector which is corresponding to the third 1 and 2. So let us find the third eigenvector. How? Choose the third eigenvector. Choose the third eigenvector, namely like A, B, C, which is pairwise orthogonal to, both x1 and x2. So this is the new concept only under the repeated eigenvalues. Because when we put x2 0, I may get the eigenvector. By putting x3 0, we may get the another eigenvector. But I do not know, there is no guarantee for that if they are pairwise orthogonal. Once they are not pairwise orthogonal, we won't able to get the diagonal matrix. So that's why for a safer side, after getting the x2, I need one more eigenvector which is corresponds to both x1 and x2 pairwise orthogonal. So let us choose A, B, C. So what's the condition for pairwise orthogonal vectors? When we say that the vectors are pairwise orthogonal, let us see that. So by using the condition x1 transpose x3 is equal to 0, x1 and x3 are pairwise orthogonal, and x2 and x3 are pairwise orthogonal, then the condition is x2 transpose x3 is equal to 0. So what about the x1? x1 transpose of 1 minus 1 1. What about x3? A, B, C is equal to 1 into A, 1 into minus B, 1 minus B plus C equal to 0, right? What about the x2? x2 is 0 1 1. So 0 1 1 and A, B, C is the x3 is equal to 0 actually. So it's equal to 0. So when I multiply this, we get 0 into A, 0A plus B into 1 plus B into C. The C into 1 equal to 0. Let us use the cross multiplication. To this step, we are getting that minus 1, 1, 1, 1, 1, 0, minus 1, 1. This gives the A value, this gives the B value, this gives the C value. So A by minus 1, B by 0 minus 1, and C by 1 minus 0. So A by minus 2, B by minus 1, C by 1. So let us multiply this by minus 1. We get capital X3 is equal to 2 1 minus 1, 2 1 minus 1. So you may have some doubt in your mind. So just pairwise orthogonal? Yeah, of course. Let us see that. Multiply x1 transpose x3, 1 into 2, 2, right? Minus 1 into 1 is minus 1, 1 into minus 1 is minus 1 is equal to 0. What about x2 into x3? Yeah, 0 into 1, 0, 1 into 1 is 1, 1 into minus 1 is minus 1, 0. That's right. So this is normally true because of we are going to choose the x3 in such a way that they are pairwise orthogonal to both x2 and x3. So now there is no doubt about whether the x1, x2, x3 are pairwise or not. There is no doubt at all because it is unfortunate. There is guarantee that they are pairwise orthogonal. Now after getting the step number 2, usually when we go for the step number 3, what is step number 3? Is pairwise orthogonal. Yes, there is no doubt at all when you go and verify that both, that is all the 3 x1, x2, x3 are pairwise orthogonal. There is no doubt at all. It is guaranteed that because we are going to choose into the way that they are pairwise orthogonal. So they are pairwise orthogonal. Mainly there is no doubt. There is no doubt. If you have doubts, please just check it out. x1 transpose x2, 1 minus 1, 1, 0, 1, 1 is equal to 0 minus 1 plus 1 equal to 0. Is right? What about x1 transpose x3? So 1 minus 1, 1 and x3 is here. I think 2, 1 minus 1 is equal to 2 minus 1 minus 1 equal to 0. And finally x2 transpose x3 is 0, 1, 1 and x3 2, 1 minus 1 is equal to 0 plus 1 minus 1 equal to 0. So anyhow these three are pairwise orthogonal. So in this video the very important concept is under the repeated eigenvalues to choose the eigenvectors which is pairwise orthogonal to both the x1 and x3. So that is a very interesting and new concept. So once we got the pairwise orthogonal, then the remaining order, what's the remaining? The remaining order usual. What's remaining? To construct the normalized model matrix. So how to construct the normalized model matrix? Before that, let us find out the length of the x1. What's the length of the x1? 1 square plus minus 1 4 square plus 1 square is equal to root 3. What about the length of x2? Length of x2 is equal to square root of 0 square plus 1 square plus 1 square root 2. What about L of x3? Is equal to 2 square plus 1 square plus minus 1 square root 6. So let us construct the n. Let us construct the n matrix that is called normalized model matrix. Let us construct the n matrix. What is the n? N is the normalized model matrix whose column vectors are nothing but the normalized eigenvectors. The first column, the first eigenvector divided by its length. So 1 by root 2 minus 1 by root 2, that is 1 by root 3 minus 1 by root 3, 1 by root 3. The second column, the second eigenvector, so 0 divides by its length, that is called normalized eigenvectors. Okay, and please go and watch the separate video I made for normalized eigenvectors and pairwise orthogonal vectors. Length of the eigenvectors as well. And the third column is the third eigenvector, normalized eigenvector. So 2 by root 6, 1 by root 6 minus 1 by root 6. So this is the normalized model matrix. This obviously they are pairwise orthogonal vectors. So n transpose n equal to n transpose equal to I. That means that n is also an orthogonal matrix. So when we get the diagonal matrix D, how we will get? We use the n matrix. What's the name of the n matrix? It's called orthogonal matrix. That's why this method is called orthogonal transformation. So what is D? D stands for n transpose n. What's the n? N is the orthogonal matrix. That's why this is called the orthogonal transformation. Got it? Now what is the D now? So let's go for D. What's the D? Yeah. The D is n transpose an. So n transpose, this is the n value. Make the transpose. So 1 by root 3. This first column becomes first row. So minus 1 by root 3, 1 by root 3. And second row becomes second column 0, 1 by root 2, 1 by root 2. A third column becomes third row, 2 by root 6, 1 by root 6, minus 1 by root 6. What's the A value? So A is a given matrix. So 2 minus 1, 1, minus 1, 2, minus 1, and 1 minus 1, 2. And once again the n, so n is as it is that. So 1 by root 3, minus 1 by root 3, 1 by root 3. 0, 1 by root 2, 1 by root 2. And this is 1 by root 6. That is 2 by root 6, 1 by root 6, minus 1 by root 6. Multiply these two first, then multiply the output with the second one. Multiply the output with the second one. So what we'll get? I think when I multiply the first one, you see that root 3 is common. So root 3 is common. 1 into 2. 2 minus 1 to minus 1 plus 1. 1 into 1 is plus 1. Is right? And root 3 is common. So this column, this second column. So once again, this is root 3. 1 into minus 1 is minus 1. Minus 1 into 2 is minus 2. 1 into minus 1 is minus 1. And third one is also once again root 3. Then 1 into 1 is 1. Minus 1 to minus 1 is plus 1. 1 into 2 is 2. Right? And again still this was there. This n was there here. Then second row with this column. So 1 by root 2. So 1 by root 2 is taken outside. 0. 0 into 2 is 0. 1 into minus 1 is minus 1. 1 into plus 1 is plus 1. 0. So it is 0. 1 into 2 is 2 plus 2. Plus 1 into minus 1 is minus 1 by root 2. The last one 0 into 1 is 0. 1 into minus 1 is minus 1. 1 into 2 is 2 by root 2. The last third row with this first column root by 6. So 1 by root 6. 2 into 2 4 minus 1 minus 1 is right. And root 6 2 into minus 1 is minus 2. 1 into plus 2 is plus 2. Minus or minus plus 1. The last one is root 6. 2 into 1 is 2. 1 into minus 1 is minus 1. Minus 1 into 2 is minus 2. Then n is already there. 1 by root 3. Minus 1 by root 3. 1 by root 3. 0. 1 by root 2. 1 by root 2. 2 by root 6. 1 by root 6. Minus 1 by root 6. Let us simplify this first. Then we can multiply with the n matrix. Okay. Let us multiply with the n matrix. Let us see that. What's the d? D is equal. First simplify this. 2 plus 1 plus 1. So 4 by root 3. This is minus 1 minus 2 minus 3. So minus 4 by root 3. This is once again plus 4 by root 3. This is 0. This is 2 minus 1. 1 by root 2. This is also 1 by root 2. And the last 4 minus 2. So 2 by root 6. Here this will cancel 1 by root 6. And that is also I think minus 1 by root 6. Minus 1 by root 6. Minus. So n is already there. What's the n? 1 by root 3 minus 1 by root 3, 1 by root 3. 0, 1 by root 2, 1 by root 2. 2 by root 6, 1 by root 6 minus 1 by root 6. Now once again multiply this two matrices. This into this. I think root 3 into root 3. Root 3 into root 3, what is that? Root 3 into root 3. Root 3 into 1 by 3. So 1 by 3 is taken outside. 4 into 1. 4 minus or minus plus 4. 4. Yeah, right. Next one. Here root 3 into this root 2. So 1 by root 6 common. 4 into 0. 0 minus 4 plus 4. Is right? Right? Yeah. Then next. This root 3 into root 6. 1 by root 18. 4 into 2, 8. Minus 4 into 1 is minus 4. 4 into minus 4. Minus 4. Yeah. Then now second row with this second column. I think so 1 by root 3 is there. There's 1 by root 3 into 1 by root 2. 1 by root 6. 0 into 1. 0. 1 into minus 1 is minus 1. 1 into 1 is plus 1. Right? Then root 2 into root 2 is 1 by 2 into 0 into 0, 0. 1 into 1 is 1. 1 into 1 is 1. Then 1 by root 2 into 1 by root 6. 1 by root 12. 0 into 2, 0. 1 into 2 is 1 into 1 is 1. 1 to minus 1 is minus 1. And the last row is root 6 into root 3. So 1 by root 18. 2 into 1 is 2. 1 into minus 1 is minus 1. Minus 1. Right? And root 6 into root 2 is 1 by root 12. 2 into 0 is 0. 1 into 1 plus 1 minus 1. Is right? Minus 1. Then finally Root 6 into root 6 is 1 by 6. Then 2 into 2, 4. 1 into 1 is 1. Minus 1 to minus 1 is plus 1. So this is the matrix multiplication. Then the final step. 4 plus 4 plus 4. 12. 12 by 3. So 4. This is 0. This is 0. Because 8 minus 8, 0. 1 minus 1, 0. 2 by 2, 1. 1 minus 1, 0. 2 minus 2, 0. 1 minus 1, 0. And 4 plus 1 plus 1, 6. 6 by 6 is 1. So have you seen that? What is the diagonal matrix? This is only the diagonal matrix whose leading diagonal elements are nothing but the eigenvalues of A. 4, 1, 1, 1. So this is the diagonal matrix. Lambda 1, lambda 2, lambda 3. This is lambda 1, this is lambda 2, this is lambda 3. So in this video, particularly, suppose the eigenvalues are repeated, how we will choose the third eigenvector x3, which is pairwise orthogonal to both x1 and x2. Both x1 and x2. So that is the very important case in this video. I hope everyone is understand this concept. Thank you so much for watching our YouTube channel. Please kindly subscribe and recommend and support our YouTube channel ADC Max. Thank you so much.